Today on Macaulay Math, we're talking implicit differentiation. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200 Calculus 1, Lesson 11 on implicit differentiation. Our goals for the day. We're going to distinguish between implicit and explicit differentiation, and we're going to find the derivative of a function implicitly. Often, functions are not defined in a simple y equals form where the dependent variable sits alone. In this lesson, functions are defined in many forms, and the methods for differentiating these forms will be explored. Let's get started.
So let's first talk about some difference between explicit differentiation and implicit differentiation. In explicit differentiation, one variable is defined in terms of a single variable. So y is equal to 3x squared, or 3x squared plus 2x plus 1. We have this single variable defined in terms of x's. And the second thing is differentiation will be by the definition variable only. So when we do the derivative of an explicit function, it will be with respect to whatever variable that function was defined by. So we will derive with respect to x because this function was defined by x. With implicit differentiation, that's a little bit different. A function can be defined in terms of multiple variables, and differentiation may be any variable, possibly even by a variable that is not in the equation. So you'll notice in this equation, our variables are x and y. In this particular differentiation, we are deriving with respect to t, because a lot of times the applications of these functions will be a derivative with respect to time. So a lot of the same properties that you've already learned in explicit differentiation will still hold true in implicit differentiation. We just have to write them a little different. One way that we can easily show the difference between implicit and explicit differentiation is by reviewing a chain rule example. In a previous lesson, if I had this function y equals the quantity x squared plus x all to the fourth power, we would say that this is the composition of two functions, an inner function x squared plus x, and an outer function something to the fourth power. And so when we did the derivative of that, we would have to do the chain rule. We would use the simple power rule on this expression here. We would bring the 4 down, leave what's inside alone, reduce the exponent by 1, and then multiply by the derivative of what's inside. An implicit differentiation version of this is very similar. Notice in this case, we still have something to the fourth power. Now, I don't know what that something is, but I can think of this u the same way I think of this x squared plus x. It is some function that is defined by whatever variable we're going to derive with respect to. In this case, we're deriving with respect to x. Since these two variables are not the same, we have to do a implicit differentiation. In the same way that we took the derivative of this expression by bringing the 4 down in front and reducing by 3, we bring the 4 down in front and reduce by 3. Then we multiply by the derivative of what's inside. Now in this particular instance, because I was deriving with respect to x, I could take the derivative of this expression. Since I don't know what this expression is, I have to have a placeholder. So this du over dx right here is the placeholder for this 2x minus 1 right there. So we just need to have that so that we know that we've completed the chain rule correctly. Guidelines for implicit differentiation. The first thing we're going to do is differentiate both sides of the equation with respect to x. In the case of related rates, we may have a different variable, but that is for the next lesson. We're going to collect all the terms involving dy over dx on the left side of the equation. We'll factor out dy over dx of the left side of the equation, and then we'll solve for dy over dx. Let's do some examples. Our first example, we're going to find dy over dx implicitly. So our first thing that we're going to do here is we're going to derive with respect to x. Okay, so we're just going to put d over dx here. So when we go to derive, we're going to derive each term separately. When we derive this first term, since this first term is in terms of x, we can derive that the way that we normally do, and it just becomes 2x. But since the variable of this second term is not the same as the variable with which we are deriving, we must do an implicit differentiation. So that thing is going to be 2 times y, the general power rule. We bring down the 2, reduce it by 1, but we have to now multiply by that placeholder dy over dx. Then we'll take the derivative of a constant, and it doesn't matter what variable we're deriving with respect to. The derivative of a constant is always 0. Now we will solve for dy over dx. Okay, so I'm going to subtract 2x from both sides. That'll give me negative 2y times dy over dx equals to negative 2x. And then we will go dy over dx is equal to negative 2x over negative 2y. The negative 2's cancel, and I'll have dy over dx equaling to x over y, and that is our derivative. Let's do another example. So we're going to find the equation of the tangent line at the given point. So we're trying to find the derivative of this expression, and then we'll find the slope, and then we'll find the tangent line. And so again, we're going to derive with respect to x. So we'll take the derivative with respect to x of the quantity x plus 2, quantity squared, let's do a better plus the quantity y plus 3, quantity squared, equals to 37. All right, so since the variables here are the same, we can do a derivative that we're used to doing. And so it'll be 2 times x plus 2 times the derivative of what's inside times 1. And again, this exponent is 1 because that was a 2 when we subtract 1. Plus, now I'm going to derive this expression with respect to x. And since those variables don't match up, I have an implicit differentiation. So I bring that 2 down like I did. I leave what's inside alone. I reduce it by 1, leave that alone. But now I have to derive y with respect to x. I'm deriving the inner function. So I have dy over dx. And that's going to equal to, the derivative of a constant is still always going to be 0. So here I'm going to solve for dy over dx. So I'm going to bring that 2 times x plus 2 to the other side. So I'll have positive 2 times y plus 3 times dy over dx equaling to negative 2 times x plus 2. Then I'm going to divide by 2 times the quantity y plus 3, and that'll leave me with dy over dx will be equal to negative 2x plus 2 over 2 times y plus 3. All right, so I am going to say that we'll just cancel the 2's, and we'll say that that is equal to x plus 2, and it's going to be negative because the negative won't cancel over y plus 3. All right, now I could do some simplification if I wanted to, but what we're doing is we're trying to find the equation of the tangent line. So I'm just going to use this 0.44 and calculate the slope of that tangent line at the point that we're trying to find. So plug in that'll give me dy over dx is equal to negative 4 plus 2 over 4 plus 3, And that will give me negative 6 over 7. So that is the slope of my tangent line. And so I'm going to find the equation of the tangent line. And we'll just use the point slope form. So y minus 4, because that's the point, that's the y value of the point. And then our negative 6 over 7 times x minus 4, because again, that is the x coordinate of the point. And then we'll just solve. So I'm going to distribute here. And that'll give me y minus 4 equals negative 6/7 x. And then it'll become positive 24 over 7. And then what I need to do here is I'll need to add 4 to both sides, but my 4 in terms of sevenths will be 28/7. So I'll have y equals negative 6 over 7 x plus 24 and 28. Well, 4 and 8 is 12, so I got to carry the 1, so I'll have 52 over 7, and that'll be the answer to that particular problem. Our final example, find dy over dx by implicit differentiation. So here we're going to derive implicitly. So d over dx of x squared y plus y squared x equal to negative 2. So I should note here there are 2 products. So I have a product of x squared and y squared and x. So I'm going to need to do the product rule twice on this thing to get it done correctly. So recall that the derivative with respect to x of f of x times g of x is equal to the first function left alone times the derivative of the second function plus the derivative of the first function times the second function left alone. So we got to do that twice. All right. So for this first expression right here, I'll have the first function left alone times the derivative of the second. Now when I derive y to no power, it just becomes the derivative of y with respect to x. To that, I'm going to add the derivative of the first expression, which will be 2x, and then I will leave the second expression alone, which will just be y. So now I've done the derivative of this first product. I'll move on to the second product. I leave the first function alone, so y squared, times the derivative of the second function, the derivative of x, is just 1. To that, I'm going to add the derivative of the first function. So it's going to be 2y now to the first, but because we're deriving with respect to x, I have to derive this variable implicitly, which means that I have to add the dy over dx. Then I am going to leave the second function alone. After that, we're going to derive the constant, and it doesn't matter what variable we derive with respect to, because this is a constant, it becomes 0. So here I want to collect terms of dy over dx on the left. So I have my x squared dy over dx. I have my plus 2y dy over dx. And then I'm going to move everything else to the other side. So since it's a plus, when I move this 2xy to the other side, it becomes negative 2xy. And when I have a plus here, so when I move this y squared, because y squared times 1 is just going to be y squared, to the other side, it also becomes negative y squared. So now I need to factor dy over dx from each term. All right, and so I can divide out dy over dx from both terms, and that'll leave me x squared plus 2y, equaling to negative 2xy minus y squared, and we'll finish it up by dividing by x squared plus 2y, and that'll leave me dy over dx is equal to negative 2xy minus y squared all over x squared minus 2y, and that has to be my last and final answer. I can't reduce anything because I don't have a common value to each of those terms, so we're going to leave that as our final answer. And so the Star Wars fun fact of the day: James Arnold Taylor, the voice actor for Obi-Wan in Star Wars The Clone Wars, shown in this animated picture here, was told not to do an impression of either Ewan McGregor, the guy who played Obi-Wan in the prequel trilogy, or of Alec Guinness, the man who played Obi-Wan in the original trilogy, but instead try and take qualities from both, since his portrayal bridges the trilogies. So his portrayal, the animated series, is between prequel and original trilogies. That's all I got for today, folks. Have a good day. Goodbye.